Chapter 2, Simulation Examples in a Spreadsheet or in Excel, Part 1. Let's see where are we now on the course map. We have completed Chapter 1, Introduction and Basic Concepts. So we learned the basic definition and terms in Chapter 1, and now we are ready to have some examples of simulation. Specifically, I can say Monte Carlo simulation and also DES, discrete event simulation, but in a way that we can do in Excel. So yeah, in this chapter 2, we are going to have some, I can say somehow simple examples that we can implement them in Excel. So we'll see how a simulation model works in Excel, but in chapter 3 and after that, we will learn the principle to model a DES, I mean discrete event simulation, in a form that we need to implement in a simulation software like Arena. Okay, so let's start chapter 2 and have some examples in Excel. Okay. So in this chapter, in order to implement the simple simulations in Excel, at first we need how we can generate random numbers and how we can generate random variables. So yeah, for any simulation model or for any simulation running, we need to generate random numbers and also random variables. Okay, so at first we'll see how we can do this, and then we'll have several examples. A Monte Carlo simulation, which will be a coin toss game, and then we'll have some discrete event simulations, but we will actually do this simulation in a way that we are able to implement them in Excel. We'll see what's the difference in between, I mean, the approach that we have in this chapter and the approach we will have in the next chapters. So yeah, we'll have a single server model, and we'll have multiple server model and also inventory and reliability models. Okay. Random number. What's random number? If we generate randomly a quantity in the unit interval between 0 and 1, then we can call that a random number. So from now on, anytime that we call a random number, we mean a number between 0 and 1, and it should be generated randomly. Okay, so any random number would be a randomly generated value between 0 and 1. Okay, so what's what's a random variable? So what's the difference between random number and random variable? A random variable will be a randomly generated quantity with a specified statistical distribution. So here it is. A random number is a number between 0 and 1 which has been generated randomly. But a random variable will have a specified statistical distribution. It shouldn't be any number between 0 and 1. It can be anything, any number, but with a specified statistical distribution. Okay, so that will be a random variable. So for generating random numbers, we have a lot of methods. So any method that generates a sequence of random numbers, it's called random number generator, or RNG. Okay. So in order to call a method as a RNG, I mean a random number generator method, that method should have two important properties. The first one is the numbers should be uniformly distributed between 0 and 1. Uniformly distributed. This means if we are actually generating several numbers between 0 and 1, let's say this is here is 0 and here is 1, then if we draw, let's say, histogram for the generated numbers between 0 and 1, let's say we group the numbers between 0 to 0.1, 0.2, up to 0.9 and 1. Okay, then if we draw a histogram, then it should be somehow uniform. I mean, equal numbers in each interval. Okay, then we can call that method as a random number generator. For example, for example, let's say we have generated 1,000 numbers, 1,000 random numbers. Okay, then we expect to have 100 numbers between 0 and 0.1, then 100 numbers between 0.1 and 0.2, and up to 100 numbers between 0.9 and 1. Okay, so yeah, for 1,000 we expect to see this, but with high probability we won't see this. Actually, if we increase the number of numbers, let's say million random numbers, 100 million random numbers, 1 million, 1 billion random numbers. So yeah, if we increase the number of random numbers that we generate with a method, then we will see exactly this behavior. I mean, the number of total numbers generated in each interval, let's say 0 to 0.1, 0.1 to 0.2, should be equal, which we call this as uniformly distributed between 0 and 1. Okay, and subsequent numbers generated should be statistically independent of all previous numbers generated. So what does this mean? This means that let's say if the previous number falls in the category of, let's say, 0.1 and 0.2, it falls in this interval. This shouldn't impact on the next number to be in this interval or any interval nearby, so close to this interval. Okay, so yeah, this means any number that we generate by a random number generator method should be completely independent of the sequence of random numbers generated previously. Okay, so yeah, this is called actually the independence property for the random number generator. Okay, so if any method has these two properties, then we can call that method as a random number generator. In Excel, we have a function called rand function, and we assume that the rand function in Excel is good enough. I mean, we can call this as RNG, random number generator. Okay, and so we can use this function in Excel to generate random numbers between 0 and 1. Okay, so let's have an example here. Simulate and predict how will be tomorrow's weather. Okay, so let's say by the historical data, we can actually estimate that the tomorrow's weather will be clear sky or cloudy with equal probability. So yeah, based on the historical data, we predict that tomorrow's weather will be clear sky with 50% chance and cloudy with 50% chance. Okay, so this is what we know by the historical data. Now, how we can simulate this? How can we simulate the tomorrow's weather by having this property that the chance between clear sky and cloudy should be equal? I mean, each 50% chance. So how can we do this? Okay. One way here is using a fair coin, right? We can toss a fair coin, then possible outcomes, we have two possible outcomes, right? Heads and tails, right? And for the fair coin, we know that the probability for having heads or tails is equal and both can happen with 50% chance, right? So since here we have two outcomes like clear sky or cloudy, and the chance or the probability for both outcomes are equal with 50% chance, so we can use tossing a fair coin to simulate tomorrow's weather, right? So we can say that if it lands up with heads, then the tomorrow's weather will be clear sky, or if it lands up with tails, then it will be cloudy. And uh, each outcome will have equal chance with the other with 50% chance. That's the one way. So another way can using a fair die, right? Yeah, we know that a fair die has 6 outcomes, right? 1, 2, 3, 4, 5, and 6. So we can say maybe we can categorize the numbers between odd and even numbers. 135 could be for the clear sky, and 246 could be for cloudy. So we actually toss a die, a fair die, and if it lands up with even numbers, then or odd numbers, then we can say what will be the tomorrow's weather with 50% chance equally, right? And or we can use a deck of cards, right? We can use a deck of cards. So how? Think about it. Or we can use Excel, the rand function in Excel. Okay, so as see here in the table, we have summarized the method. If you use a coin, then heads will be for clear sky, tails will be for cloudy. If you use a die, then 1, 3, and or 5 would be for clear sky, 2, 4, 6 would be for cloudy. If you use a deck of cards, then any red card or any black card. Any red card will mention tomorrow's weather will be clear sky, or any black card will mention tomorrow's weather as cloudy, okay? Or we can use computer, I mean the rand function in computer. So in Excel, for example, rand function generates a randomly number between 0 and 1. So we can say if this random number generated by the Excel is between 0 to 0.5, then tomorrow's weather will be clear sky. Or if it's greater than 0.5 but less than or equal to 1, then tomorrow's weather will be cloudy. Again, both with equal chance, 50% probability. Okay, so yeah, Excel rand actually will be the function for generating a random number. Okay, so let's have an example here, a Monte Carlo simulation, which is called a coin tossing game. Okay, a coin tossing game. So in this game, Charlotte tosses a coin for her friends Harry and Tom. Okay, exactly 100 times. Okay, so Charlotte tosses a coin for Harry and Tom exactly 100 times. So Harry wins $1 when head lands up, and Tom loses $1. So when the coin lands up with heads, then Tom should pay $1 to Harry. So Harry wins $1, Tom loses that dollar. But if the coin lands up with tails, then Tom wins $1. This means that Harry should pay $1 to Tom. Okay, so this is the game. So Charlotte tracks their respective wins and losses as they play the game on any toss. So on any toss, Charlotte will determine if Harry is ahead or Tom is ahead, or maybe they are even. Okay. So now what's the question? What's the question of this game, and why we are going to simulate this game? On any game of exactly 100 tosses, it's is it more likely that both Harry and Tom are each ahead about half of the tosses? Or is it more likely that one of the two is ahead most of the times. So yeah, that's the question, right? Do we expect to see exactly the same numbers? I mean, half of the tosses that Tom is ahead or Harry is ahead, or is it more likely that one of the two, I mean, Harry or Tom is ahead most of the times? So let's see what's the answer for this question. We're going to answer this question uh, by having a simulation model for this game. Okay. Or yeah, let's to be more specific, we mean that Harry and Tom are each ahead about half of the tosses. I mean, for example, Harry's ahead in on 45 to 55 tosses, and thus the Tom is also ahead on 45 to 55 tosses. So in this case, they will be somehow equal on the number of being ahead. Is this the case? Or Harry is ahead most of the times. For example, Harry is ahead on 95 or more tosses. Or vice versa, Harry is ahead on 5 or fewer tosses. So yeah, this is our question, and we're going to answer this question by having a simulation model in Excel. Okay. So let's see how we are going to implement this game as a simulation model in Excel. Okay. So the first step is generate a task. So you need to generate a task in the Excel. So to do so, we can use the rand function in Excel. So in Excel, rand function will generate a random number with uniform distribution between 0 and 1. So we can call this as a random number generator. Okay. So by having this rand function, any number can be generated between 0 to 1. So we can decide on the head or tail if, let's say, R, the number generated by the rand function, is between 0 to 0.5, then we can decide that the outcome of the toss is head. And if it's between 0.5 to 1, then it will be tails. Okay, so this is how we generate a toss in the game in Excel. Okay, so the second step is find the toss winner. So if the outcome of the toss is heads, then Harry gets $1 from Tom. And if it's tail, then Tom gets $1 from Harry. Okay, then yeah, this is the rule, and this is how we compute the winning. If Harry's winning is greater than Tom's winning at ith toss, then at ith toss, Harry is ahead. I mean, the total winning so far at ith toss, if the total winnings of Harry is greater than Tom's, then we actually say that Harry is ahead. But if the total winnings of Tom is greater than Harry's at ith toss, then Tom is ahead. Otherwise, they will be even. Okay, so this is how we determine who is the winner or who is the ahead at ith toss. Okay, and so, and we need to repeat this these two steps 1 and 2, for 100 times. This is the game, right? And at the end, we will compute the probabilities for Harry being ahead, even with, or behind Tom. So the question here is 100 tosses enough in order to compute the probabilities? You will see in Excel, by having just 100 replication, let's say 100 100 replications of the game, it's not enough, because anytime that you rerun the game, the results change. So you'll see there that 100 game toss is not enough. So you may increase it to 400 times, for example, or 1,000 times. Or we may go for replications. We can, let's say we can set the game with 100 tosses, and then we can replicate the game 1,000 times, for example. I mean, anytime we will have 100 tosses, right? So then you will see by having more and more replications, the results become more constant. And then at that time, we can say now we can rely on the results and we can calculate the probabilities, okay? So we will see this model in Excel in the next part, okay? By having the simulation model in Excel, we can try different scenarios. For example, we can see what if the coin is biased, not a fair coin. For example, the probability of having heads is, let's say, 0.73, for example. And the tail would be 1 minus p. I mean, it will be 0.27, for example, right? And or we can say maybe the winning decision changes for each and every coin toss. For example, Harry wins when head lands up on even toss games, or else Tom wins, for example. Or Tom wins when heads lands up on odd toss games, or else Harry wins. So yeah, by having a social model, we can try all these scenarios to see what will be the impact on the final result. Or for example, what if the game is played with a fair die, 6-faced, and then Harry wins if the die outcome is 5 or 6, right? Or else Tom wins. And what if the die used is biased and the winning decision is randomized for each and every tosses? Again, different scenario, okay? Or what if we use two dice, a fair and biased die in the game? So for example, Harry wins if the sum of the two dice outcome is greater than 9, or else Tom wins. Or Tom wins if the sum of the two dice outcome is greater than 7, or else Harry wins, and so on. So yeah, by having the simulation model in Excel or in Arena, we can try all these scenarios, and then after that we can compare the results, that which game will ends up with more winnings, for example, for Harry, or more winnings for Tom, for example. Okay, so we will see that you can try all these scenarios. But yeah, in the next part, in part 2 of the video, we will see the simulation model in Excel for the base model, but you can try all these scenarios in that file as well. Okay, so that we'll see in the next part. Okay, thank you.